To prove that the maximum value of the 2 norm over all x with the 2 norm of x being equal to 1 is the largest singular value of a, we start by doing a singular value decomposition. For a vector x, we can write the singular value decomposition as follows. The 2 norm of the singular value decomposition and the other side is as follows. Since u is orthogonal, we have the following relationship. Let z equal to v transpose x. We can do this because v is orthogonal. Then we can then write our expression as follows. To find the max norm, we know that sigma is a diagonal matrix with singular values sigma 1, 2 through r. Knowing this, we can write the expression as follows. Maximizing the 2 norm of ax equal to sigma z 2 norm under the constraint of the 2 norm of x being equal to the 2 norm of z equal to 1, we find that z is equal to 1, 0, 0, 0 transpose. Knowing this, we see that the 2 norm of ax is in fact equal to the largest singular value. And thus we have completed the proof. The maximum value of the 2 norm of ax over all x, with the 2 norm of x being equal to 1, is the largest singular value of a, sigma 1. Now we consider the differential equation x dot is equal to f of x, where f of x is the following vector. Taking the Jacobian of this vector with the 4 partials with respect to x1 and x2 and f1 and f2, we get the following Jacobian. We know that the vector x has to be less than r, therefore both entries x1 and x2 are both less than r. Knowing these two qualities, we see that the magnitude of the Jacobian satisfies the following inequality. Since both x1 and x2 are smaller than r, we can replace x2 and x1 with r and take the absolute value of each term. Simplifying leads to 4r plus 2. Since the Jacobian is bounded by 4r plus 2, it satisfies the Lipschitz continuity definition, where L is equal to 4r plus 2. Therefore, the Lipschitz constant is 4r plus 2. To prove that the vector differential equation x dot is equal to matrix A times x plus matrix B times u with the initial condition at time equals 0 equal to x naught has both a solution and a unique solution, we must prove the following two conditions. The function of f must be piecewise continuous in T, and the function of f must satisfy the Lipschitz continuity in X. Starting with piecewise continuity in T, we know by assumption from the question that AT and BT are both piecewise continuous. The input u of t is also piecewise continuous. Therefore, b of t times u of t is piecewise continuous. Because the right-hand side of the differential equation is completely piecewise continuous, the left side is also piecewise continuous. Therefore, we've proved f of x and t is piecewise continuous in T. The second condition, Lipschitz condition, says that there must be a constant L that satisfies this inequality for all t bigger than 0. If we plug in our vector differential equation into the Lipschitz condition formula, we see, and simplify, we see that f of tx1 minus f of tx2 is equal to a of t multiplied by x1 minus x2. Taking the norm of both sides, and then using a known property of norms, we can take the a of t out of the right-hand side to get the following inequality. we see then that because a of t is finite because it is piecewise continuous, it satisfies the constant, the Lipschitz constant L for the Lipschitz continuity equation. This proves that f of t of x is Lipschitz continuous in x. Therefore, overall, since f of t of x is piecewise continuous in t and Lipschitz continuous in x, there exists a unique solution x of t. To find the solution of x dot of t equal to a x of t with initial condition v, we can use the general solution of a linear time invariant system, which is the matrix exponential times the initial condition. To put this in the form of the initial condition times a scalar function of time, which we'll call alpha, we can use the definition of the matrix exponential, which is the following infinite sum. Knowing that v is an eigenvector of A, we see that the corresponding eigenvalue lambda satisfies the eigenvalue property listed here. We also know that a to the exponent k times the eigenvector v is equal to the eigenvalue to the power of k times that same eigenvector. Using this property, we can substitute the eigenvalue into our matrix exponential. Following the substitution and simplifying, we see that e to the power of at is also equal to e to the power of lambda t. Therefore, we can write our general solution as x of t is equal to e to the power of lambda t times the initial condition v, where alpha t is equal to e to the power of lambda t. In order to find the solution to our linear time invariant system when our input u of t is equal to e to the power of t times v, we can use the general solution of a linear time invariant system with a known input u of t. Therefore, our solution x of t is equal to the state transition matrix times the initial condition plus the integral of our state transition matrix times our input integrated over tau. Plugging in our state transition matrix, which is e to the power of at, we get the following expression. Because from 3.1 we realize that we can replace e to the power of at with e to the power of lambda t, a scalar function of time multiplied by v, we get the following expression. Simplifying the integral, we can pull out e to the power of lambda t. We can do a u substitution to solve the integral. Solving the integral and pulling out the common term v from each term, we get the following expression. We can then simplify the contents inside the parentheses and we get our general solution x of t. Which is e to the power of t minus lambda e to the lambda t over 1 minus lambda times our initial condition v. This is for the case when lambda is not equal to 1. If lambda is equal to 1, then changing the integral slightly, we have the following solution. X of t is equal to e to the power of lambda t plus t times e to the power of lambda t, and then all of that multiplied by our initial condition v. And that completes this question.